Let's rattle off a big list of all sorts of things that people argue about in statistics. For example, how are you going to handle your data? Do you want to keep it hidden and just show the results, or publish it out? Realize that you're not required to actually give out your data in order to publish, but maybe other people could see it and do cool stuff with it. Maybe some of the cool stuff they would do is some paper that you might have been able to get to in the future, but isn't that what science does? And maybe they're going to figure out that you did something wrong and they won't like it. And if that's true, is that good for science? Which should remind you of some of the ethics that we talked about before. And it's easy to say, oh, one of these sides is right or wrong, but keep in mind, one side is saying, I keep my data because this is how I feed my family and this is what my children need to stay in our home. And the other side saying, no, but this is for the good of science and all of humanity. So I don't know which one is better. Personally, I would prefer it to be on the open side, but not where people have to worry about their job if you find out that they did something wrong. And I don't know that society's there yet. Theoretical versus applied, this is a big deal in academia, but even if you're part of a research company, there might be experts who know all the theory behind things. That's valuable because if something changes, like one of those base assumptions, they're going to have an idea of where to go and what needs to be changed to do it next. Whereas someone who's more on the applied side is okay with things that are messy or not the cookie cutter kind of assignments that you see in homework assignments. They often get viewed as being more useful, so there's not a right or wrong here. You may have to pick which side you're on, and it's going to depend on which classes you gravitate towards and where your skill set is. Mean versus median is something you talk about in the intro class. If it's symmetric, then of course they line up. The mean is going to have more power as it accounts for all the data. But if it's highly skewed, the median might give you a better feel for where the actual middle of the data is, and the mean gets pulled off by the high skew. And you should be rolling your eyes. Yeah, we talked about this in intro class. Okay, but just like you might try to decide between mean and median, you might try to decide between standard deviation and IQR, or there's something called the mean absolute deviation. When I was in an intro class, squaring these before you added them up and then square rooting it back, why can't we just do the absolute value? Well, you can actually. It has a name. It's this thing here. Why do we like standard deviation? On a bell curve, the standard deviation goes from the mean out to one standard deviation, which is really nice to draw on a graph. But on a normal bell curve, the mean absolute deviation is just a constant times that S. So we really could use one or the other and get away with it. Why do we always pick this guy? Because that's what people have been doing forever. Why did that start out as the tradition? Here's the equation for the normal distribution, and notice sigma, which is estimated with S, is showing up here. If we use the mean absolute deviation instead, then you'd have to have this square root of pi halves constant that would figure in there and make it look a little bit uglier. But is it worth it? Because this just makes so much more sense to me, as I think it would to people who didn't know statistics. But are you going to choose tradition and go with the vocabulary and notation and terminology that people have used for a long time, or try to delve into something new? I don't know. I'll tell you, I still teach S in the intro class because that's what we are asked to do. Histograms is a can of worms. Look at this data. Does this look like the right histogram? Or should we make the bin smaller so that you can see there's actually a lot tighter in? Or should we make the bin smaller so that you can see this exponential nature? Or maybe the bins shouldn't be equal at all. Really skinny bins on this end and wider bins on that end. You can really get statisticians arguing about the right way to do a histogram. The point is, we're trying to convey information to the client. The answer is going to be whichever one does that based off what they understand and what they need to know. A lot of these choices are about two competing sides, and the null and the alternative hypothesis fits in here because you can make decisions that support one or the other. Now, the null hypothesis is what you assume by default, okay? So if you're unsure, if you don't have a lot of data, the null hypothesis wins. The alternative is typically what you want to show because this is the stuff that gets published. It's what's interesting. So the alternative hypothesis is what you're hoping is true, but if you're unsure, it defaults to the null. So often what people have is a model and choices that give the null hypothesis every chance you can. That way, if you still reject, now you can be strong and say, oh yeah, it is definitely supposed to be the alternative hypothesis, and then you feel like what you're publishing is actually true. So, for example, in the intro class, when we're talking about degrees of freedom, we tell them to just take the smallest degrees of freedom. Now, Satterthwaite weight is a better method, but this is simpler for the intro class, and it gives the null hypothesis more strength. Like, you're more likely to fail to reject. That way, if you reject, you can be like, oh yeah, I'm totally sure that you should be able to reject correctly. But what if you really want to get published? You might decide to do something else. For example, saying, my t distribution is so close to a z, does it really matter? We can justify it by saying I have enough data to switch from t to z, and because I switch from t to z, now the alternative hypothesis is more likely to be rejected. That's because the z distribution is skinnier, less error than the t distribution. Small change that favors the alternative makes it a little more likely to be published, and people actually do this because they're choosing to support the hypothesis they want. And yeah, this goes back to the ethics issue, choices that you've got to make. Let's talk about a scenario here, and then when we're done, I'll have you talk about the video post, which error you think is worse. You see someone who's homeless. Your null hypothesis, we're going to say that he is truly homeless, hard on his luck, having a tough time. Alternative, he's actually a scammer who's quite wealthy and just begs because he can make more money doing that than other jobs. We can either choose to donate some money, we're just going to say $100, I don't know, it doesn't matter, or we can ignore him. If he really has no money, which we don't get to choose whether he's actually homeless or actually a scam artist, but if he really has no money, we want to give him the money. That makes us feel good. We're helping someone who's in need. Let's say that he's a scam artist and we ignore him. Well, we're going to say that that's also a good scenario because we don't want to support someone who is earning a dishonest living. There's two types of errors that can happen. One is he really is homeless and we're like, oh, I'll bet he's a scam artist. Well, now you're a jerk. Or he's a scam artist and we give him money and now you're stupid. So which one do you feel like is worse? There's no judgment here. The hope is that this is just a scenario that you can relate to and that people will have an opinion. Some people on one side, some people on the other. Is it worse to give to a scam artist or to pass up a homeless person? Just tell us your own personal thoughts. And whatever you say, it might change where your line is as you talk to this person or inspect them. Some people are going to say we should shrink our alpha so that we only assume they're a scam artist if we're absolutely sure, oh, look, I can see some, fancy watch or whatever else. Some people say push the line in, have a larger alpha, so that if there's any evidence that he's a scam artist, we're going to say, yeah, no. And not judging which one you pick, just an opportunity to practice moving that alpha. This shows up in research. For example, some companies have to choose between safety and cost, or future benefits and current risk, things like that. So this isn't just a silly scenario. This type of decision process is actually pretty common. Let's talk about doing a data set and does the alpha matter? Well, here I've got a whole bunch of, it looks like variables to predict anxiety. And some of them are highly significant. Others aren't significant at the 0.05 level, but a little bit less. So you could raise or shrink your alpha. If you change your alpha from 0.05 to 0.03, it's going to make things simpler. This variable would stay, but that variable will drop out. So lowering your alpha gives you a smaller, more easy to manage model, something a little simpler. If you raised your alpha, said, I'm going to use 0.1, these terms here are going to pop in as being significant. It's going to give you a larger model, more to research, more things to help you predict. Your goal here is going to have a big influence on which direction you choose to go with those alphas. Are you hoping for a big model with lots of things or a small model with a very few simple things? On the final project, I do not specify what alpha you have to use. So if you're wanting a larger or smaller model, you might adjust that alpha. I do ask you to be ethical about it, okay? Don't just change your alpha to get you the model you want. Actually think about what your goals are and move from there. Hypothesis tests and confidence intervals kind of have a little bit of fight, and there is currently a debate on should we only do one or the other, and there's some rationality behind this. Hypothesis testing, you get that p-value. How strong do you support that particular null hypothesis? It is the traditional one that people like, and it's meant to only say, is this specific model good or not? So basically, how likely is the data given the model I'm creating? Confidence intervals, you get an interval. All the values in this interval are considered reasonable values, and we don't really, when we do confidence intervals, say that any values in that interval are more likely than others. It's just everything in this interval we're okay with. You can use it to make decisions, same as a hypothesis test. And if you know there's a difference and you want to estimate that difference, confidence intervals make sense. And it's asking what models are likely based on the data, which is the flip side of the hypothesis test question. So people argue, could we use just one or the other? And I think the answer is yes. Personally, I wouldn't mind if confidence intervals won the battle, but there's a lot of tradition, so I don't think we'll see this resolved for 30 years at least.